I'm going to present our ICCV work, Adversarial Attacks are Reversible with Natural Supervision. Deep networks are vulnerable under adversarial attacks. One can easily craft invisible perturbations to fool the state-of-the-art classifier. There are many methods that defend against adversarial attacks, but they all focus on improving the robustness with robust training algorithm. For example, adversarial training augments the training data with adversarial examples. Model regularization trains the model with additional constraints, and adding more tasks at training time improves robustness. However, even the strongest defended models are still vulnerable under attacks. On the state-of-the-art robust model, invisible perturbations still subverts a canon to traffic light. This is because the model is burdened at training time, and they cannot find a single representation that also works for all unforeseen corruptions and attacks. We ask this question: can we develop an inference time defense that can adapt to the attack? Our key insight is that images contain incidental structure. For example, using the structure, we can tell which two image crops are from the same instance. And we can use the structure to tell how much the image is rotated. Our key finding is that adversarial attack not only cause the image classifier to fail, but also damage the incidental structure of the image. We show the loss that indicate the natural structure of the images. And we can see the attack increases the loss from blue to orange, which means the attack damages the input structure. Our key idea is that we can reverse the attack by fixing the natural structure of the images. We now introduce our method. We first train a separate self-supervision model on natural images. We only optimize the yellow part. We train a contrastive loss to discriminate which two patches are from the same image. When adversarial perturbations are added to the input, they all corrupt the image structure that is used to predict the self-supervised task, causing the self-supervision task to fail. Our method optimizes input via gradient descent so that the self-supervision task is fixed. By decreasing the loss, our method restores the natural structure of the input. After our reversal, we can correct the adversarial attack and provide a more robust defense than all existing approaches. Even if the attacker is aware of our defense, our method is still robust. We show a lose-lose situation for the attacker. If the attacker ignores our defense improves accuracy. If the attacker adapts to our defense, it will hurt the attack and increase our robust accuracy. In addition, we can theoretically prove that our method can improve the robust accuracy. Please check our paper for details. Empirically, our method improves robustness on CFR 10 by over 7%, CFR 100 by 5%, SVHN by 11%, and ImageNet by 3%. Even under unseen attacks with larger perturbation bound, our defense is still effective. From green to red is a gain after adding our defense. In addition, our method achieves a better trade-off between the robustness and clean accuracy. We lastly visualize the feature trajectories under our method. The attack moves the feature from green to red, causing misprediction, and our method brings the red back to the blue and correct the attack. To conclude, we propose an inference time defense for adversarial attacks by restoring the intrinsic structure of the input. Our method achieves a state-of-the-art defense on the auto attack leaderboard. Our test time defense method is generic, which is compatible with existing training time defense method, and can be used in other modalities such as sound, language, and beyond. We also publish our code. Thank you for listening.